All right, so we're going to pick off most of the way through what we did on Monday. And I'm going to start with these blank gears that we set up using our global equations to run both the input gear, the output gear, and then the back plate. And we can see here we have our equations. And just to play around with this a little bit and demonstrate how this was working, we can change the gear ratio, save this file, update the assembly, and all the parts in the assembly will automatically update. And we can edit kind of any of these if we want. We're not really changing these last two because they're just equations that we're using to drive the actual parameters, but they are there. If we wanted to use a different equation, we could. Just that is what maintains the appropriate sizing of each of the gears. So that's kind of where we're at. And the first thing we're going to do is we're going to demonstrate how to make a set of teeth that have a simple cross-sectional profile, just to show kind of the principle there. And then we're going to go to an involute tooth profile, which is what you would want to use if you're actually trying to make some gears that meshed and worked well. Okay. All right. I'm going to start by opening up the input gear. I'm also actually going to close the assembly because every time I make an edit to the input gear, it's going to want to try and update that assembly file. And especially when I go to turn my input gear into an output gear, I don't want conflicts to cause issues or lag while I'm doing that. So I'm going to close my assembly before I start making edits to my input gear. So with my input gear opened and my assembly closed, I want to draw out the sizing that I'm going to use for my gear. And to do that, I wanted to share with you all. I've updated the overview documentation and added a few reference figures in there that kind of describe the profile of a normal involute gear relative to the nominal diameter of the gear, as well as the addendum or the top plane and the dedendum, the bottom plane. So we have this top land and the bottom land. Zoom out enough you can actually see that. There's the bottom land there. We don't really want those two pieces to touch. We really only want the faces of the gears to interact with each other. And the involute portion of the gear is going to go from this working depth bottom line here, the blue one, up to that top green line. This back line where we have the clearance, as you can kind of see here, there's a clearance gap there, really doesn't matter because, again, since nothing's touching that space, nothing should be touching that space, it's really there to make sure that we don't have extra friction inside the assembly that would try and push the gears apart as opposed to transfer motion. That makes sense? So it doesn't produce any additional unnecessary force or torque inside the gear set. So we're going to draw out each of these kind of dashed lines on our profile, and then we'll put the tooth profile on top of that. And really what we're drawing is we're drawing the cutout version of that tooth profile. If we wanted to do the additive portion, we could start with something on this clearance line and then build out from that. But it's usually easier to cut in than it is to build out. And if you go back to like this old Tony video talking about making gears, you're never going to deposit a gear tooth onto a steel blank. You're going to start with a steel blank that has the size of the top land as the perimeter, and then you're going to cut the tooth into it. And so doing it this way is more reminiscent of the actual manufacturing process. And where possible, you really want your SolidWorks models to mimic those processes because it helps to translate it into manufacturing if the things you do in SolidWorks kind of have a one-to-one relation to the actual manufacturing processes. And as we get to computer-aided manufacturing, you'll see the relationship between the features in SolidWorks to the actual finished geometry and how those things can interact with each other. So let's go back into SolidWorks. I'm going to do a sketch on the front plane. And I want all of those circles that we had from our worksheet. So there's 1, 2, 3, 4 circles. The top one here is actually going to be the extra parameter on the outside of the circle. And then we're going to come to our actual pitch or actual effective diameter, come in from that, and then we're going to offset down. So I'm going to draw 4 circles on my SolidWorks sketch. So there's the outer one. There's the effective diameter. There's the dedendum. And then there's the clearance circle. And then I'm going to dimension each of these relative to my die-in global variable that I specified already. So this outer one is going to be equal to my die-in plus 1/2 my pitch. So I'm just going to do global variables pitch divided by 2. And this is a little bit kind of before what we ended last time. And I'm going to go and I'm going to modify the blank to be bigger in a second. The next one I want to be just the actual effective diameter. So I'm going to specify that. I'm going to get equal to global variables, my die-in. And you can see that matches the current size of the blank. The next one I want to be equal to my effective diameter minus my pitch divided by 2. That's going to be my dedendum. And then this one, I just want to have a clearance. I'm going to use a 1/100th of an inch clearance between the dedendum, the one I just drew, and my my clearance line. So you can see those 3 sizes there. And what I'm going to do is I'm going to turn these into center lines, so that way they are just references that I can use as I draw my gear profile onto this part. And really the reason I'm doing this differently than when we did it last time is I want to try to use the same profile for multiple tooth cutouts, but I don't want my cutouts to actually change the geometry of these lines. So hopefully that'll make sense. I'm going to make these all construction lines. The second to last one, this one is the die-in minus 1/2 of pitch. So it's the effective diameter plus 1/2 of pitch, the effective diameter minus 1/2 of pitch, and then a 1/100th of an inch clearance.
So why 1/2 of pitch?
For this one, it doesn't really matter since we're not going to be using these lines as solid lines, but by making them construction, it's easier for me to visually differentiate the outline that I'm going to use for the cutout from the guides that I have here as a reference. And the reason I'm using plus or minus 1/2 of a pitch is it makes the height of the tooth proportional to the pitch of the tooth. And so the aspect ratio, the length to width of the tooth will be reasonable. It doesn't have to be, the height of the tooth and the pitch don't have to be the same. You could have longer, skinnier teeth, and you could have shorter, stubbier teeth. But if you start going to extremes on that, where your pitch and your tooth height are wildly different, it's not going to mesh because the teeth will hit each other basically, right? Or if they're not deep enough, if they're really fat, you're going to have like a very small contact area because that tooth is so shallow, right? Yeah. So there's reasons, but they're somewhat arbitrary. And you could optimize those to figure out what the appropriate size is. The hard thing there is that if you start varying that significantly, you need to make sure that that variance is consistent across all of your gears. So you have to pick something that's going to work for a small gear and a big gear. And we'll see how that becomes a problem, especially with this Flintstone gear meshing here pretty soon. Okay. So I'm going to accept that. As I just mentioned, I need this blank to be the size of this larger diameter, right? So I'm going to edit this sketch. I'm going to right click on Boss Extrude 1, click on Edit Sketch. And then I'm just going to edit this equation so that way it's diam plus pitch divided by 2. And if I wanted to, I could have done those guiding lines as the first sketch and change the order and then reference that initial line. But I'm not that concerned about that. And so now you can see that my outer diameter, right, my top land diameter and my tooth or my blank are the same size. Questions on that? Does that make sense? Okay. So now I'm going to actually draw the tooth cutout that I want to use. I'm going to do another sketch on the front plane. I'm still using the front plane because if I use the front plane, then I am more resilient to change in the future, because if the extrude of my blank changes, that doesn't change the position of the front plane. And so it's easier for me to not get caught up in trees where something is dependent on something, which is dependent on something, which is dependent on something that can cause longer errors that are harder to fix. I'm going to convert my top edge and my bottom edge to solid lines. And then what I want to do is I want to make two angled lines that go across my part. And I want a point which intersects those angled lines and my effective diameter, because that's where I want to set the pitch of the cutout, or really half of the pitch. I'm going to do this on the top just for convenience. And then I'm also going to do a vertical center line that goes up through my part, because I want to mirror this line so it's the same on both sides of that line. And if you're doing this horizontally as opposed to vertically, it doesn't matter. So that's going to be 1/2 of my cutout. And I want to point at the intersection between this line here and this tooth face. So I actually didn't get the intersection relation there. So I'm going to click on that point, hold Control, click on the line, click on my center line, and make that on the intersection. And then what I'm going to do is I'm going to mirror that line and the point about my center line. Oh, I didn't get what I wanted. I'm going to highlight both of those, click on the mirror entities tool. Doesn't want to let me do it. There we go. And then I'm going to mirror about my center line. I'm going to accept that. Now, the reason I want to do that mirror is now those two faces are the same. And I can specify the distance between this point at my effective diameter and this other point also at my effective diameter, and make that equal to 1/2 of the pitch. And then all I have to do is specify what angle I want these lines to be at. Let me leave the Smart Dimension tool. I'm just going to drag this out a little bit. And I'm going to set that to 60 degrees.
Sorry, you already said that.
Yeah, and I'll do this whole thing one more time after I finish it, in case you guys need to do it. The nice thing about having those center lines being on that back plane is now you see when I cut through that top and that bottom line, I get these segments for my outline of my trapezoid, and I can still have those full complete center lines in the background. I've done this a couple of times now, just planning for the class, and that's the way that I resolved this being the cleanest. All right, I'm gonna do that one more time. So if you guys got a little bit behind, I'm just gonna start over back at the start of this sketch. So I'm gonna exit this discard. Again, starting from my guidelines, I'm doing a new sketch on the front plane. I'm gonna convert the top line, not offset, and the bottom line. I'm going to draw a vertical center line, which I'll then use to do the mirror. I do want that to be vertical through the origin of my part. And then I'm going to do a horizontal, or not a horizontal, a diagonal line kind of coming across this portion. I don't really care what the size of that is right now. And then I want to point at the intersection between this effective diameter and my diagonal line. So I'm going to put that point there, exit the point tool, hold Control to get the point in those two lines to make it at the intersection. And then I'm going to mirror. Yeah, so to get that point to be at the intersection between these two lines, I click on the point, hold Control, click on the two lines, and then an intersection is one of the relations I can add. And that'll put the point on the intersection of those two lines. Once I've got those where I want it to, I can move those around if I want to. I can angle it if I want to get it closer to where I want it. I don't really need to do that, but it can be helpful. I'm going to mirror both the point and the line about this center line. And you can kind of see how that's going to make the other side of this cutout. And then once I've got that mirror in place, I'm going to go ahead and specify the width between the two lines at that intersection point as being half of my pitch. And then I do want this is going to be a cutout, so I want it to come wider. So I'm going to exit the Smart Dimension tool, kind of widen that up a little bit. and then specify the angle between these two lines as 60 degrees. Trim away the excess circles. And now I've got a single closed contour. It's not really a trapezoid because it has arcs on the top and the bottom, but it's basically a trapezoidal tooth. Because again, those top faces and the bottom faces are not touching. So even if they were square, it wouldn't change the performance of the gear thanks to that clearance. This one here, that's half of the pitch. Yeah, so I did global variable, I did equal to global variable pitch divided by 2. Anyone got questions on that one? We're good? All right, I'm gonna click OK. Go into features, I'm gonna extrude cut this part. Since it's on the back, I need to flip and make sure it's going in the right direction. And I wanna do through all. You can see I get a cutout for one tooth. Pretty straightforward. If you want to hide your sketch here, you can. I'm actually gonna leave mine shown because I'm gonna use that to drive the gear relation when I put this back into my assembly. Because now I've lost that exterior face that I was driving it before is now too big. And so it's not gonna have the appropriate gear ratio. I need to use one of those center lines for my effective diameter to drive that. And we'll probably get an error when we go to do that, but we'll get to that in a second. All I need to do now is pattern this. So I'm gonna do a circular pattern. The direction, I'm gonna use the, Martha. Yeah, so on here, sorry, in the cut extrude, the two lines that were going around, I trimmed that. So you just have the top section and the bottom section. And so all I have is 2 arcs, the top and the bottom, and then the 2 side lines left over. If you don't trim them, you can always select the contour that you want to use for the cutout. But I prefer not to do that because it's less resilient to changes in the future. Did that get it, Marza? You good? Okay. So again, we're going to go to the circular pattern. For the direction, I'm going to use the central shaft of the gear. I want to use equal spacing over 360 degrees. And I want to calculate the number of teeth based off of the perimeter of the gear. So I'm going to use equal to global variables diameter in times pi, that's my perimeter, divided by the pitch. That'll give me the number of teeth. Now this is going to round. And one of the things that I didn't account for in the worksheet, but that we should account for is the fact that this could potentially round down and end up not having enough of a gap. So if you imagine that you have a certain pitch that doesn't round to an even number, and I round the number of teeth down, now I'm going to have not enough spacing. My teeth are going to be too wide and the space is going to be too narrow. They won't mesh. So I'm going to add 0.5 to this. So that way, if it's done around, it's always going to round up, which means that worst case scenario, my gap for my teeth is a little too wide. And if you have to err on the side of clearance versus interference, err on the side of clearance, right? Does that make sense? If you're designing for something, if it's going to be varying, you probably want your variance to result in a clearance and not an interference, especially if you want things to move, right? Like I want these things to mesh and then to move relative to each other. If the teeth interfere with each other, that's never going to work, right? They have to have some clearance around them. Anyone have questions on that? Did that work out for everybody? I'm going to go back into the edit feature. Make sure you have equal spacing. Make sure you have 360 degrees, and make sure you have the die in times pi divided by pitch plus 0.5. So 0.5, if you want to be a little bit more explicit there. And it should look appropriate. Anyone not getting a good looking gear? You just practice SolidWorks. Let me know when you're back up, Reed. If you want to, you can also just download the Flintstone gear. After we do the next part, we're actually going to leave this and go on to the involute, so it's not a big deal. All right, so I want to make this gear in into my gear out. So I'm going to save this. So it's saved. I'm going to do save it as gear out. I'm going to replace gear out. And this is one of the reasons why I want to make sure I have that assembly closed, because if it was open right now, it would just throw me a bunch of errors. And I'm going to do tools, equations. And then in my dimensions for this part, I'm going to change all of my diameter ins to diameter outs. And then this is just a lot faster than going through and remaking the whole gear profile. And be careful you don't miss any or misspell them. Yeah, I saved it. I did save as. I selected my gear out, and now I'm editing all my equations. And I'll bring that up again if need be. So there's my gear out. I'll save that. Again, I went to File, Save As, selected my gear out, hit Save. And then in Tools, Equations, scroll down and make sure all the die ins get replaced with die out. Because that's the only difference between my input gear and my output gear, is that I'm driving the diameter of the gear to set all the parameters other than the pitch. So diameter and pitch is all I'm using, right? See, die out, pitch, die out, pitch, die out, pitch, die out, pitch, die out, pitch. I guess in pi, but pi is a global thing. It doesn't change. Once I've saved my gear out, now I can go back in and I can open my assembly and resolve the issues that come up with the fact that I don't have the same geometry that I did. So I'm gonna hit rebuild. It's probably gonna complain that, hey, something went wrong. And you can see that it did. And on the mate, for the gear mate that I had up here before, see there's an issue that the edge I was originally using no longer exists. So what I'm gonna do is I'm just gonna delete that gear mate. And I'm just gonna make a new gear mate to replace it. I could also edit the gear mate to fix it. And that'd be fine too. Before I mate the gears together, I wanna make sure that the teeth are meshing close as possible. These are Flintstone teeth, so they're not gonna mesh very perfectly, but not too bad. And so I'll go into my mate tool, go into mechanical. I'm gonna unclick that face, click gear. Now what I want to do is I want to use the center line that represents the effective diameter of the gear as the entities for this mate. So you see those two center lines meet right there. Those are the two that I want to use. And then once I have that, I can exit the mate tool and you can see that they do move the way I expect them to. And they mesh, kind of okay. You can see the thing that Tony was talking about in the video from last time, where here's the contact point on the very edge of the tooth, and it's still on the edge of the tooth, edge of the tooth, edge of the tooth, and now the whole face is in contact at the same time, and now the contact has shifted to the opposite point on the opposite tooth, right? So you kind of see that overlap transitioning from one to the next, and how that would induce a large amount of vibrations. I'm gonna hide the sketch in here so that's a little easier to see. So let's hide that. And then just kind of run through that again. Now, another thing that we want to do is we want to check and see how resilient this is to gear ratios. So let's try gear ratio of 4. And that's pretty significant for just a regular spur gear. And you can see that that caused me errors. It still calculated everything, but one of the mate got messed up. My gears still are working okay. I'm not sure specifically which equation it's complaining about. It doesn't show an error in equations, although it says error in equations here. So I'm not sure exactly what's complaining there. And it seems like it's running okay. And you can see that the number of teeth in those gears did update properly. If I go to the extremes on this, I can break it. So there's a 10-to-1. See, my teeth are getting to the point where they're almost the size of my part, but it actually holds up pretty well, all things considered, right? Woo. That's a little too big for just a straight spear gear combination. A 10-to-1 ratio is real significant. Once you get to ratios that are that high, you're probably looking at using a combination of gears, right? If I want a 9-to-1 ratio, I can use 2 3-to-1s and probably have about the same efficiency as a 9-to-1. Once you get higher than that, you're definitely going to be more efficient using multiple gear sets than using a single gear set. Maintaining the appropriate contact is difficult once those differences get very, very large. Okay. Yeah. This one actually does not have a contact. We're just using the mates to cause them to rotate at a proportional rate. So if I look at this carefully, you can see that the gears are actually going into each other, right? They're just moving at something close to the appropriate relative rate. That makes sense? And that's a lot more computationally easy to do than doing an actual simulated contact. Sound good? I'm actually, it's not telling me where the error is and it's still running fine, so I'm just ignoring it. I'm okay with that. I don't know if you guys, maybe you're not. I'm gonna go back to my 2-to-1 just so these are reasonable. Yeah, I don't see an error. In any of these things. So it seems to be working okay. I'm just gonna ignore it. All right, so like we talked about before, these trapezoidal gears, the flat face gears, are not going to be efficient in transmitting torque because of that kind of movement of the contact angle and the contact location in a sporadic way. So if we use an involute gear, we should be able to get a much more consistent pressure angle. And so our torque transmission will be nearly constant, which is much better than having vibrations inside the system, especially if you're trying to transmit high power. If you're doing really low power systems, it doesn't really matter that much, especially if they're moving slow. But if it's fast, high power, like a motor, like an engine for a car, it's turning at thousands of RPMs with, potentially several hundred foot-pounds of torque, right? At the same time, that's going to be a problem. And if you're designing a power plant where you're doing, megawatts of power, you're going to tear a gear like this apart in fractions of a millisecond. It's just going to get destroyed right away. So we need better gears than this. So let's go back into our input gear. I'm going to open up that part. Once that opens again, I'm going to go ahead and close the assembly just like I did last time. If it crashes, then I'll just close SolidWorks and open just the part. Sure, I'll save all so they all update. It's fine. I have this open a couple of times here. This is my output gear. I'm going to close that. That's my input gear. I'm just going to check real quick to make sure I don't have anything else open. Yeah, we're good. And then I'm going to delete my cut extrude. Bye-bye. And then I'm going to edit my sketch for that. Actually, I'm going to show my background sketch first. And what I want to do is I'm going to actually replace, I'm going to take this whole thing out. If I was thinking in advance, I probably would have suppressed that and left it there. And then I could have toggled back and forth. Yeah, I can always hit the undo. Undo is my friend, I guess, right? There you go. Let's do that. I'm going to suppress this cut extrude. So that way we can pretend like it's not there. Roll back before my circular pattern. No, we'll just stay there. That's fine. We can just do the pattern again. And then I'm going to show my pattern, my center lines that I had before. And I'm going to sketch back on the front plane. Now this time, because of the equations I'm going to use, I'm actually going to come down here to the right. It's not going to work unless you're on the right side based off the equations I specified inside the worksheet. So the most important thing for this one is to get that involute profile to add to my gear. Did you guys all feel like you had a pretty good idea of what the involute profile, how that's generated from the video and things? I'm just going to show you the blue quick clip art. I was looking for something that more described as an involute spline. It's all gears. There we go. So you can see an involute pattern. This is what an involute pattern. If you imagine a string wrapped around the circle, when I unwind the string, that's the path that I get. And then that path of that kind of unwinding is the curve I want to use for the contact face of my gear, because it leads to that constant pressure angle, which you can see in the GIF that we have there. Right? And again, the contact speed here is really not what's staying constant. It's really the torque that is constant. Right? And so if you look at the distance to the force on both of these gears, it's going to be the same. All right, so let's generate that. Wrong one. So to get that spline, what I need to do is I need to use an equation-driven curve, which is not on my default options here. Whenever you want to use an obscure function in SolidWorks, I recommend just searching for it. So I'm going to type EQU. There it goes, equation-driven curve. Everybody see that? If you don't see this pull up, there are options as to what you're searching for in this dropdown. So there's commands or help. Make sure you're on commands. And then when you do your EQU, you should see equation-driven curve come up. Anyone not seeing that? All right, so click on that. We want to use a parametric equation. And then we have two functions. I'm going to scroll down because I don't have them memorized. This is too zoomed in. And we are here. So this portion here, the 0.5 cosine t plus t sine t, that's the part that I'm most concerned with. This D2 at sketch 2, I'm not sure that's what I want to use. I'm actually going to exit this real quick. And I want to use this size right here. That is sketch 2, but the size for that is this one. So you can see that on mine, it is D2 at sketch 2, but go into yours and make sure that yours is whatever it is. It is, but it won't let you use diameter in the equation-driven spline. I tried it. I don't know why it doesn't work. I looked on YouTube to see if there was something I was doing wrong. And they said the same thing, that it doesn't work and you need to use the dimension. So in my equation-driven curve, I'm going back into that. I'm going to use my parametric, paste that in for the X. I'm going to paste it in again for the Y, and then I'm just going to change the cosine to sine, the plus to a minus, and the sine to a cosine. And then for my parameters here, I'm going to go from 0 to 1. And then when I click off of that, it should show me the involute curve. I actually want this to start at the D-dendum, so I used the wrong one, maybe D3. Yeah, use D3. Use the D-dendum one. I wanted to start at the base, that kind of, not the clearance line, but the D-dendum line. I could try it again to see if I can use my die-in. I would actually want to use die-in minus pitch. Oh, is it working now? Minus pitch. It's buy-in minus pitch divided by 2. Oh, is that going to work? I would love it if that worked. Oh, it did work. Use that equation instead. That's much better. Die-in, the die-in has to be in quotes, minus pitch in quotes divided by 2. That whole quantity in parentheses times 0.5. Zero. There's like a zoom in function I can use in like Windows, right? No. Magnifying glass? Magnifier. Oh boy. Is that better? You guys can read that out. I'll leave that up there for a few seconds so you can get typed in. I don't know why that didn't work when I did it at my office. Interesting. Maybe it's because I put equals. Because whenever I do equations, I always do equals, blah, 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 blah. Maybe it just doesn't take the equals. That could be it. Of course, maybe I should try and actually accept this curve before I assume that it's working. How do I exit the magnifier? That's a... Let me check and make sure this actually generates. Okay, yeah, it generated. I can bring it back up too. You want me to magnify it again? Yeah, so the cosine becomes sine, the sine becomes cosine. Instead of plus t, it becomes minus t. Now, I want to do a word of warning. Once you input that curve, it will allow you to take that curve and move it around however you want in SolidWorks. So that we don't accidentally move this curve after we've created it, the first thing I want to do is fix that in place. So I'm going to click on the curve, and then there should be an option here to add the fix relation. And that's going to prevent me from accidentally dragging or moving that curve around and breaking all the work I did to get that nice involute profile. Okay. Yeah. I have T2 as pitch times 4. Which one?
Down a little bit.
Oh, I just made it shorter so it fit on the screen better. We're going to cut off that end anyways, so don't worry about it. Yeah. I just need to make sure that regardless of how big I make this, it goes out past this addendum line. Yeah. So don't worry about that. That's not a problem. All right. I'm going to convert my inside circle here and my outside circle just like I did last time. That's going to become the top and the bottom of my cutout. I'm going to add a very short little line segment going from the, waiting for SolidWorks to respond, from the end of my arc horizontally to my clearance line, the one I just converted. And now you'll note that this curve is starting kind of on the x-axis, and that makes the equations a lot simpler. I can come up with an equation for how to generate that curve at an angle, but I don't want to, and I don't have to. So I'm going to cheat just a little bit here. And what I'm going to do is I want to draw a center line that goes from my origin off to my effective diameter line. And then what I'm going to do is I'm going to put the end point of that line at the intersection between these two curves. So I'm going to exit the line tool, click on that end point, hold control, click on my effective diameter and my involute profile, and then make that at the intersection. Now I'm going to make another center line that just goes down below that one. Does anyone need me to do that one again? Real quick. Is that pretty straightforward? I'm going to assume that we're okay. I'm going to do it. Your center line? Oh, the involute curve, just fix it. So if you click on it and click on the fix button, it should turn black. Good. Just turn out vertical. So don't click on the point, click on the line itself. your involute curve is coming out vertical?
Yeah,
Did you X the Y plot? You want to multiply that whole thing times, you want to multiply each of those by minus this one. That doesn't look right. All right, so just delete it. Going to a new equation driven line and compare metric. So to die, so yeah. Die in, yep, and then outside the next parenthesis, you want to do minus. So inside this part here, like before the times 0.5, and after, there you go. Do minus, and then quote pitch. Close parenthesis there, and then put this die in inside of parenthesis. So it's that whole quantity times that. Copy and paste that whole thing. Then 3 clicks to it, and just drag it across. Change the cosine to a sine. Change the plus to a minus. This plus right here. And then change that sine to a cosine. And then make it go from 0 to 1. You see it generate. Good. Okay.
Yeah, so it looks like yours. Mine's
So that center line that I have there is not horizontal. Got it. You just need to add energy. That one. Why didn't you say something?
Oh, because you were way ahead. I had a bunch of errors, but I fixed them.
Okay.
It's
Well,
okay.
we are recording this,
I know.
so we can go back and take a look at this. I do want to finish it before we end the class time today. One thing that I will say, I want you guys to have these parts done and submitted for the week by the end of Friday. So if you want to use your Friday time to get help finishing these parts, then that's okay too. Okay. All right, so I want to mirror this just like I did the last one, but I'm going to mirror it at an angle so I don't have to do math. So I'm just going to draw another center line that goes from my center down to my contact point. I'm going to exit that. And what I'm going to do is I'm going to mirror my little kind of clearance line and my involute curve about that center line. Actually, I'm going to do my extra center line too, so I get that point. I clicked the wrong things. Let's try again. Mirror. I want to mirror this guy, and this guy about this guy. There we go. Yeah, it's just saying like, hey, I'm mirroring that spline. I'm not going to mirror the equation. I'm just going to do a geometry pattern basically, which is fine. And then since this one can be messed up, if I drag it around, I'm going to fix it right off the bat. And then actually, no, actually I want to set my angle first or my pitch first. What I'm going to do is I'm going to go in and I'm going to smart dimension the distance between these two. And I'm making it equal to my pitch divided by 2. And then I'm going to fix it. You can see that kind of locks everything in place. Now I'm going to trim off all my excess. You notice I have a little bit of an excess here that I need to trim. And I'm not going to worry about this little segment here. Although if I want it to line up just right, what I can do is I can make it coincident with my origin. And then that'll give it the same relative angle as that horizontal line at the top. And then that gives me my nice involute profile for my gears. So I'm going to go into features. I'm doing extrude cut. And I'm going to flip this. So it's going through all in the direction of my gear. And then the pattern is exactly the same as last time, circular pattern. The center of the hole becomes the axis. And I'm going to use the same equation as last time, global variables, diameter in. times pi divided by pitch. And I'm going to add plus 0.5, so I always round up and not down. So honestly, this is as far as I was able to get before class. I want to save this. I'm going to save it regular first. So let's save. I want to do save as to copy this into my output gear. And I want to be able to just go into tools, equations, and change all my die-ins to die-outs. But when I did that last time, it complained to me. And I think it's because I have all those equations in my sketch. Yeah. That I would need to update as well. So I don't think this is going to work. I just want to try. Yeah, so that broke it. So the problem with that is my equations that I use for these patterns are no longer valid because they're using that original profile. I was able to unfix them and it looks like they went to the right location, but they still don't have the right starting point. If I do die out on this instead of die in, I might be able to regenerate them. But honestly, I think I'd rather just go through and like redraw this. Yeah, because it's breaking all my stuff. So what I would do here is I would just delete this profile. Why don't you want to come up with your horizontal? I'm just extending this curves a little bit. Do a new involute with the same process. So I'll go back to my equation driven sketch. Curve. Type in my equation again as my out this time. Times 0.5 times cosine of t plus t times sine. If I get this whole equation right from memory, I'll be proud of myself. This would be sine. This would be minus cosine from 0 to 1. There we go. Got it. Boom, like that. Then I'll just fix these guys here. Intersection. Oh, no. That's why I wanted to fix this curve first. So fix this one so it doesn't move around. Then I can add this as the intersection between these two lines. There we go. Now I'll add my little tail for my clearance. And I can mirror. Gives me the same error. Again, I don't care. Oh, I gotta trim off my excess. Nope, wrong button. Getting a little over ear because I know we're running low on time here. Pitch divided by 4 for the spacing? That should give you the same thing. Yeah, because you did it between the center line that you're mirroring about and the point. Yeah, that'll be fine. Yeah. It'll work out to the same thing. So there's my output gear, and I'll save it. A little bit of extra work because of that involute and it not updating with the equations. I don't know why you can't put that equation into like the actual equations list, but SolidWorks doesn't like it. Last thing I'll do is I'll take a look at my assembly. You see my gears are a little bit offset. I have to suppress my gear mate for a second. And then I'll try and get these lined up kind of nice. And I'll unsuppress it. And now you can kind of see that that contact is a nice smooth transition as the gears go down. What's that? Oh. I guess. Yeah, come and have a seat. I think that's the right spot. I'm not for sure, but we're just wrapping up.
Oh, okay. Oh, wait, so it's not this class?
Not this class, but this is 3:30. So, or this is 3:39.
Oh, okay. I guess we'll just wait because they're probably gonna have another class in here. I'm so sorry.
That's okay. All right, so I'm gonna call it a day there.